Hadi Ali Akbarian, Associate Professor from KN2C University of Technology in Tehran, and also my laboratory wireless time measurements lab. And I'm going to introduce you or talk today about my presentation entitled From 4G base station antenna elements toward hybrid sub-6 GHz 5G base station antennas. I will very quickly introduce my group and what we are doing in our laboratory, and then a little bit of background theory and to introduce why we are talking about BTS, or let's say sub-6 GHz 5G BTS antenna elements, and then about some theory of integration of antennas that we are doing, and then followed by some simulation and fabrication results. Very quickly, we have quite good, well-equipped laboratory which is called Wireless Terminals Measurement Lab, or in abbreviation VTEM. We are mostly focused, right now, we are focused on antenna projects due to the project that we have right now, but currently and previously we have been working on material characterization and some EMC projects, as well as some projects regarding applied electromagnetics. But my project, we have facilities such as vector net analyzer 4 ports from Rohde and Schwarz up to 40 gigahertz, and we have other devices that are quite useful for us in doing measurements. Also, I can point out the probes, electric field probes from NARDA up to for 18 gigahertz, and also my team, brilliant team, let's say, which is for the moment managed by my student Reza Asadi, and the whole team are doing very well. So I start my introduction part with the need for co-site solutions in BTS antennas. Co-site solution is a big issue for operators when they want actually to operate more than one generation of mobile telecommunication system, let's say 2G, 3G, and 4G at least, simultaneously in one BTS, and even many of them have both TDD and FDD bands together. And now with the presence of sub-6 GHz 5G, they have to add even more complexity to it, and they have to integrate antennas as much as they can so that they can actually present these services in one BTS. You see, for example, here in this central picture, two section of one BTS antenna. One part is for FDD channels, one part for TD channels. This is actually an example of this separation. Or even here up right, we have lower bands at the right, then upper band at the left, 3.3 to 3.8 gigahertz, and in the center we have mid band, let's say 1.71 up to 2.7 gigahertz. So it's a kind of just separation of space that is available in one BTS between antenna elements. And for example, here at the left, you see let's say the lead of one BTS, where you have all of the output ports from one BTS. You see multiple. This tells us that we have integration issue. We have to integrate all services in a small area in a BTS, which is normally limited in size. And as an example, inside a typical BTS antenna, you can see number of different antenna elements which are placed adjacent to each other You see, for example, lower band antennas, higher band antennas, the smaller one, and then even some of these high band inside lower band one. And this is actually something that has been an issue from many years ago. But before that, I want to introduce that in one BTS antenna, we have multiple subsystems. Antenna elements is in various bands and a number of different antenna elements are at the last part of this subsystems. We have feed network behind it, which is used to feed these antenna elements. In the feed network, we have mechanical phase shifters, which is one important issue. We have power splitter combiners. We have filters and duplexers, which is before or after this feed network. We have a system which is called remote electrical tilt to control phase shifters. We have cables and connectors connecting these devices to each other. We have the tray, radome, and other mechanical parts, which are also important in the design. And we have currently calibration system inside it in BTS antennas, which are most of them you can see in these photos, which, for example, in the back part, in the front side of the BTS, you see this antenna element. Here have brought a typical technical specifications of a BTS antenna, where you see multiple bands. For example, here we have at the left the 1.4 to 2.7 gigahertz band, and here at the right 700 to 960 megahertz band. And from each of them you have two rows of antennas, so you have multiple output ports from the one BTS, and you have two for each of them. You have plus minus 45 degrees polarization, to two polarization per each array of antennas. And then you have gains, which is normally defined by the size of the BTS, other factors, cross polarization ratio, interband isolation, VSW, which is normally 1.5, etc. And here at the I just want to add that recently we have this band added to it, 2.3 to 3.8 gigahertz, which is also used in 5G sub-6 gigahertz. We see that we have this band added to the BTS antennas, which is also covers N77 and N78 from FR1 band of 5G new radio. And these antennas, this BTS is called hybrid BTS. Why? Because then they have to simultaneously give services to the older band and the new bands of 5G. But this is not the only thing which is added to these BTSs. We have other technologies which are added to it. We have 88R technology, which is useful for beamforming. We have three different beams, which I will shortly discuss. We have much higher number of output ports. Previously it was, for example, 8 ports, but now we're talking about 22 ports out of one BTS. For example, this is this schematic of two BTSs, the older one and the new one. But both of them has the same width or size, more or less the same size. They are always around 50 centimeter, but now we have much more antennas and bands added in it. So we have an issue of integration. We have to integrate more antennas, more bands inside this more or less the same area, and so we have to place antennas in another form. We have to use the area more efficiently, and also we have to use another element, to add another element from 2.3 to 3.8 gigahertz, which is also about 50% of bandwidth, which is more or less the same as the bandwidth that we had in our previous bands. The bandwidth is not much here, but the antenna is a little bit different, as it is not only broadband, but also it has a higher frequency, so that's more sensitive to fabrication. It is more difficult to fabricate it, and also we have higher loss in materials. Also, we have other services added to it, in other technologies. First of all, mechanical phase shifters, which are mostly used in this kind of BTSs, now they have to be redesigned. But for example, some companies now are using cable-less designs. They want to remove cables, so they have to integrate antenna with phase shifter. And also the use of beamforming technology, as I said, not only we have single column beam from out of one array of antennas, but also we have service beam which should be able to rotate or steer the beam. We have broadcast beam for mostly, which is used. I mean, this broadcast beam is used, and I highlighted them because they are the topic of another presentation. I just keep them and go to the part about the antenna element. But here also, I want to add two more technologies. First, the other one is MCIC connectors, which are now called MQ4 or MQ5 connectors, which are actually, which combines 4 or 5 coaxial cables inside one cable, because we have a problem of cabling. There are lots of cables inside the BTS. Now with this, they can actually really minimize it out from 4 cables. You can create one. Okay, here I start with the designs for the low band elements. So there are two types of low band elements. The first type, you can see some of them here, the papers and the designs are kind of sequentially rotated 4 dipole arrays. These are sequentially rotated and then combined in a kind of feed network. And this is one of the things. Normally they're like they're similar to a kind of bowl or something like that. And then we have other types of low band designs, which are cross dipole schemes. So there are 2 dipoles which are cross each other, and then have very good performance. You see the 3 examples of that here as well. But for mid-band, which is normally from either 1.7 to 2.7 gigahertz, or which is the second one, which is wider band, from 1.4 gigahertz up to 2.7 gigahertz. Again, we normally use cross dipoles, but these are kind of cross dipoles which are sometimes called 4-leaf. You see 4 leaves which are attached to each other in a cross dipole format. And nearly most of the designs in this mid band, which is previously high band, but now we call it mid band because we have another band on top, are made of such elements. And then previously, let's say, when they wanted to combine these two in one space, and either they put it next to each other, or sometimes are combined in different formats. One element, a higher band element, is placed inside, as you see here, inside the low band element, center to center. And then, as the low band element has longer wavelengths, we have a space in between each of them to put another high band element that can actually give us a higher gain, for example, in higher band and compared to lower band. And sometimes we can actually have 3 high band elements out of every 3, actually every between each 2 elements of low band. So we have other configurations, but most of the time in the BTSs they use such classic one. We have in between each low band elements we have one high band added. So this is a kind of a solution to use the area more efficiently. But when we come to high band, let's say from 2.23 to 3.8, we don't have that much of published papers or technical reports about it. But we have many products in the market that have such designs, but not that much of papers. So this is actually one of the designs that we have. In fact, we fabricated that. You see a kind of four-leaf design. So mostly or normally, the design concepts which have been used in mid-band between 1.4 to 2.7 just scaled down to be used in 2.3 to 3.8 gigahertz. You can see here. But as I said, because of the sensitivity to fabrication, the one trend is to try to design antennas with contactless, let's say, configurations, such as the one which is brought here in this paper. They try to use, for example, aperture coupling instead of, for example, directly feeding the upper element either with coax or with PCB. But we have a problem of bandwidth here, but it can't actually cover the whole 2.3 to 3.8 gigahertz band. And just one more point, and here in these cross dipoles, you see here, you have actually two dipoles combined. One electrical dipole, which is out of one dipole, electrical dipole, but in between each dipole you have the kind of magnetic dipole, which from the combination of these two electric dipoles and magnetic dipoles, you can have a better radiation pattern, and this is the concept that is used in such antennas. Now let's move on to theory. Actually, the motivation of this work is that now with the presence of three bands inside one BTS, the traditional types of combining, integrating antennas next to each other does not work anymore. And we have to think of a more efficient solution where antennas share the same area for either two or even three bands. As you can see here, for example, in this design, we have to have in this BTS, we have to have four high band elements in 25 centimeter on top or bottom of one low band element. So that's not actually a thing that can be done by the previous types of designs. So you can see here inside some of the BTS antenna, the photos that can be also seen in internet. The solution is to stack antennas on top or bottom of each other. You have to really go toward higher integration and use of this area in a way that one antenna can be put on top of the other one. And for example, here, these low band antennas on top of high band antennas, here also the same thing, and here, which normally actually the low band is on top of the high band, and can be seen in schematics of it, can be found in some actually technical notes. But in terms of theory, this can happen actually. If you search in published works, you can see how they can do that. You can see here that one low band antenna is put on top of four high bands, and you can see here that the current on the top from the high band antenna is induced on the low band on top of the antenna, and the pattern is distorted. So this mutual effect and mutual coupling between the two destroys the radiation pattern of the both antennas, mostly the high band antenna on the bottom. What is the solution? For example, this work from Sun suggests that if you put a kind of filter, low pass filter, inside, or the distributed filter inside the low band antenna on top, you can actually decouple, or let's say decouple the high band current in the low band one, and let's say prevent it from radiating, and therefore destroying the radiation pattern of the high band antenna. So if you see here, we did it's kind of meander line and capacitors implemented inside each arms of this dipole, low band dipole. You can have this kind of filter, distributed filter, which at the end resulting in a much better radiation pattern. You see that now the radiation pattern of the antenna on the high band antenna, which is at the bottom, is not deteriorated. And you see here that, for example, the antenna, the high band antenna alone is fine. When you put the low band antenna, the pattern is the radiation of the E field is altered. But when you put this filter in it, then it is back to the normal radiation. And there are other actually types of putting this low pass filter in it in the low band antenna. Because here is, you can see you have this cross dipole, but you put a spiral radiator. You put these spirals inside these arms, and this creates an inductor and a capacitor, which in total creates a low pass filter and does the same thing as the previous work from Sun, and this one is from another IEEE MTT paper. And at the end, I want to put this one also, it's actually from patent from Comscope company. You see here that they have put antennas, they're integrated on all of them very efficiently. They put antennas, low band antennas on top of the others, and you see here they have put a meander line, it's an inductor and a capacitor. You see, this is the top side, this is the bottom side. It is an array of inductors, capacitors, which creates a low pass filters, kind of low pass filter, which prevents the let's say the induction of the high frequency current from the bottom antenna on the top antenna. But this filter does not do anything in the lower band. The lower band antenna is radiates as more or less as previously done. So going to the simulation, this is actually the first antenna we've simulated. It's a simple 4-leaf antenna, but we put it in an FR4, but this is not actually very high-tech antenna. It works from 2.3 to up to more than 4 gigahertz. The reflection is fine. The radiation pattern is, the gain actually is quite good between in the first band, the lower band and the higher band, between 2.3 up to 2.7, and here from 3.3 up to 3.8. So this antenna is then put at the bottom of sequentially rotated 4-dipole. You see that in a normal, kind of a classical low band antenna, but you see that the radiation pattern is failed and it cannot be used anymore. So this classical way is not working. Another example of putting another 4-leaf antenna, we've put that here beneath another 4 let's say sequentially rotated 4-dipole antenna. Does the same thing and deteriorates the radiation pattern. So let's move on to classical cross-dipole design, which goes from 700 to 960, and then we designed it. And put it on top of our high band antenna, but not on top, but it is still close to it, not on top, but affects it. You see here that the pattern is actually deteriorated. We compared the radiation, but again, it's the gain of the high band antenna, but not the gain and the peak, but the minimum gain of the antenna in a cone of 60 degrees. You see, because the antenna normally should have a 60-degree beam width, so we put the minimum of this gain in this cone as the reference on top. You see in the top plots, and then the minimum gain of the antenna after placing the low band next to it, and at the bottom you see here that this has been reduced by 2-3 dBs, especially at the lower and the higher band, which is important for us because from 2.7 to 3.3 is not actually out of the band. So these two parts you see still the reduction in the gain because of this effect. As a solution, we have tried to create this this inductor and capacitor inside this cross dipole. You see the placement of one capacitor that is not actually worked very well. But when we put these inductors and capacitors on top and bottom of this cross dipole, you see that here we have improved the minimum realized gain in both, but not all of them, but most of them here at the bottom side and the top side, and then here. Only we have problems here in one of these plots, and then these plots are the gain of each of these two antennas, high band antennas, and in each polarization. So in total we have 4 gain plots that you can see here. One of them is still not working, which we later actually fixed it. You see here that now the result is much better. So we have been successful in putting the antenna, the low band antenna on top of high band antenna. We have even tried that when the antenna is placed beneath the low band, and it's still working. You see here the radiation pattern before and after placing the antenna. Here in 2.3, 2.7, 3.3, and 2.8, it's still more or less the same. It does not deteriorate it a lot actually, and this is actually final design. One of our final designs. You see here, as you see here, and even we tried other configurations with the same antenna, which worked quite well. And you see here some of the radiation patterns before and after placing the low band antenna on top of the high band. The antenna is fabricated, and this example, for example, is fabricated with quite well reflection and radiation pattern, and we also fabricated the high band antenna. And this is actually one of a complete BTS design. We have tried to have this integration. This is similar to one of these data sheets that I'll show you. The integration of low band antennas with mid band, and the integration of high band antennas with the high band antennas with low band. And that is the theory that should be used in the new generation of BTS antennas for higher degree of integration. As a conclusion, I said that we have the new technologies in sub-6 GHz 5G BTS antennas, which is called hybrid actually BTSs. We have higher integration, we have beamforming, we have calibration, new phase shifters should be deployed, and these technologies which should be deployed are already deployed actually in BTS, and there is still room for more research in it. And the most important part of it that we have discussed a little bit more is the space sharing between the higher space sharing between these antenna elements. That is one of the challenges that should be under research in the future.